In this lecture, I want to introduce some terms having to do with experimental design and then introduce the two basic types of experimental design: completely randomized design and blocked design. In ecology, we often use the terms manipulative experiments versus quasi-experiment versus observational or mensurative experiments. So by manipulative experiments, what I'll mean is situations where treatments are randomly assigned to experimental units. And if everything is done correctly, the great thing about manipulative experiments is that you can actually incur cause effect. You can make a strong statement that the treatment that you apply actually causes the effect that you observe. Quasi-experiments, on the other hand, are situations where treatments are not assigned randomly. It might be a sedimentation event that occurs in a stream, and you want to look at the effects of that sedimentation on, say, stream invertebrates. You did not actually impose the treatment in this case. It happened naturally, and then you're looking at the effects. Cause effect in that situation is confounded. There's other factors that could be creeping into it in this situation, so you have to be careful. And then finally, what I'll refer to as observational, mensurative, uncontrolled, or correlative approaches are situations where you do not do any manipulation at all as the observer. You simply examine associations between the dependent or response variable and the independent variables that you think may be influencing it. You cannot occur cause and effect in this situation. Oftentimes you'll see scientists try to infer a cause-effect relationship, but you have to be very, very careful. Now the problem is that you'll see all different classifications of experiments, quasi-experiments, and correlative studies in the literature, and I'm not going to try to go through all of these. This is a figure out of your textbook that was put together by Eberhardt and Thomas back in 1991, and it relates directly to the categories that I talked about, but uses different terminology. So, for instance, they talk about events being controlled by the observer, and in that case, I would refer to those as manipulative experiments, right? Situations where you have distinct perturbation that occurs that was not implemented by the experimenter, then they refer to those as distinct perturbation events. I would refer to those as quasi-experiments. And then finally, you have a third class of uncontrolled events where there is no distinct perturbation, in which case you're really talking about an observational study. I like to use these terms manipulative experiment, quasi-experiment, and observational study because I think they're much more intuitive, and in some instances you'll see the term, for instance, observational experiment. Well, to me that is confusing. So I will only use, or try to only use, the term experiment where I'm talking about a situation where there's actually been a manipulation by the observer, or there's been a distinct perturbation that is then examined by the observer. So if we focus first on manipulative experiments, what are the characteristics that make up what we would consider a good experiment? Well, there's really three things. First is control, second is randomization, and third is replication. And I use this picture of mesocosms here because this is a situation where we can often do very nice manipulative experiments. We can create these mesocosms, which are basically just little baby swimming pools filled with water and usually some litter to simulate, say, small ponds. And then we can look at how different combinations of amphibians, for instance, influence the growth rate of animals in these ponds. So we can control our treatments, we can randomly assign them, and we can get lots of replications. So what do we mean by control? Control provides a basis for comparison, a standard against which changes in the experimental treatment group can be measured. So a very basic component of any experimental design. The second component is randomization, and by this we mean the process by which experimental units are selected. So by using a random design in assigning treatment, it eliminates selection effects and allows assumption of independence and eliminates bias. We know, for instance, from this example where we might have petri dishes where we're assigning some sort of treatment, it's very possible that there could be a temperature gradient from the wall to the open walkway. And if we were to assign all of the treatments of fertilizer 1 close to the wall, fertilizer 2 in the next set of units, and no fertilizer out by the open walkway, it's very possible that we could be confounding our treatment effects with a existing gradient in our experimental area. And so it's crucial to use randomization to eliminate bias and allow assumption of independence among our experimental units. And then finally, replication. We have to have replication to allow an estimate of experimental error. And by looking at the summed effects across a treatment group, it allows estimation of a mean effect. And this is a critical component of any experiment, and often something that we run into difficulty with in natural resources and ecology, because oftentimes we want to impose treatments over large areas. That incurs a lot of cost, which then often results in reducing the number of replicates of a particular treatment, which then makes it, in many cases, more difficult to actually estimate an effect of our treatment.
Before we move on and talk about the term experimental error, I want to say a few things about the term experimental unit, which unfortunately isn't well defined in your textbook. So we'll use this definition. Experimental unit is the physical entity which can be assigned at random to a treatment. And of course, this is going to depend on the kind of experiment that you're doing. So probably the example we're most familiar with is maybe an individual animal. Maybe in this case you're working on white-tailed deer and you're injecting them with some compound that will reduce fertility, because we know that especially in the eastern U.S. there's a problem with overpopulation of white-tailed deer, and so they're experimenting with different approaches to trying to reduce fertility rates. In that case, it's pretty clear what the experimental unit is. It's an individual animal, and then you might look at birth rates from those tagged and injected deer over time. Another example that applies to a lot of the kinds of things we do in natural resource science is a situation where you're looking at maybe the impacts of grazing on vegetation, biomass, growth, whatever it might be. Now, this is a situation where sometimes you find that we get into trouble with our definition of experimental units, and we're going to get into this more later when we talk about pseudo-replication and some of Hurlbert's ideas. But say you're interested in the impact of grazing on plant productivity. Now, what you'd like to do is go and find a whole population of pastures and then randomly assign a number of those pastures to different grazing treatments. That can be logistically really difficult because these pastures might be big, it's difficult to find cooperators and that sort of thing. So sometimes there's a thought, well, let's just impose my grazing treatment in one pasture and we'll go out and take a bunch of different measurements in that pasture and call those all different experimental units. The problem is that doesn't incorporate the pasture to pasture variation. And so really all you can talk about is what has happened in that pasture and you can't generalize anywhere else. This kind of situation often comes up too with large, say, lake-wide experiments where you might be putting some compound in to reduce algal growth, for instance, and you go and you take a bunch of samples and again think, well, this is these samples are my different experimental units. Really, they're not. The experimental unit is the lake, and the samples that you take, multiple samples you take from one lake would be what are sometimes referred to as observational units. That's a term that's used in your text, and I like that definition. Sometimes those will be referred to as sampling units, and that gets really confusing because we've already talked about sample units when we're talking about sampling as independent samples from an area you're interested in. In this case, sample unit is really referring to a subsample, and these would be samples that are drawn from a single experimental unit. It's fine to do that. There's going to be variation in your lake, there's variation in your pasture. So if you want to go and take additional observational units, those are fine. It's how those are treated when you do your statistical analyses that can get us into trouble. So the important thing with an experimental unit is that each unit is actually independent from one another. And again, especially when we get into large landscape level kinds of experiments in ecology, it's often difficult to get multiple experimental units in a system.
So now that I've brought up this term experimental error, let's talk a little bit more about exactly what we mean by experimental error. Experimental error describes a failure of two identically treated experimental units to yield identical results. Experimental error occurs from a variety of factors. One might be measurement error. If we're measuring the wing of a bird, one person might measure the wing and they could hand that bird to another person, ask them to measure it, and they may get different measurements even on the same bird wing. So simply differences in individuals and how they read instruments or how they apply those instruments and so on. There could also be inherent differences among experimental units that then result in experimental error. So we know individual animals differ in their genetics, age, sex, the environment they grew up in, and so on. And so those all of those things may affect how they respond to some treatment. We know that there may be differences among plots. If we're looking at the growth of some plant species, the growth of that species is not going to be uniform everywhere. It is influenced by the soil, elevation aspect, cover of other plants, and so on. Even in that mesocosm example that I showed you, where it looks like you could perhaps have experimental units that are all very, very similar, and you might expect whatever you're measuring in each of those mesocosms to respond in a similar way. But we know that there can be position effects depending on where a mesocosm occurs in the array, maybe get more or less sunlight. Water depth may vary. Organic material may vary in terms of the amount or the origin, and the individual animals that you place in those mesocosms as you're experimental units may also have inherent differences. So there's lots of different ways that experimental error can creep into our experiments. Oftentimes with experimental design, what we're trying to do is to implement designs in order to reduce experimental error so we have a better chance of observing the treatment effects that we're interested in. Our goal, of course, is to make valid inferences regarding the conclusions of an experiment. And there's two effects that should be considered here. One is what we call internal validity, and the other is external validity. Internal validity refers to correctly concluding that an independent variable is in fact responsible for a change in the dependent variable. So basically making sure that there is good experimental design used in the study. And that's what we've been talking about in this lecture. External validity refers to the ability to generalize the research findings to a target population, and this is important, not beyond. So oftentimes we'll do a study in some small area, maybe one particular district of the BLM or Forest Service, or even our own backyard, and say, well, this applies to these species across their entire range. Got to be really, really careful about that, because we all know that there's different environments, and that can affect what the outcome is of a study, whether it be a correlative study or an experimental study. But oftentimes you'll see in the discussion that people will make inferences to the entire state or the entire range of a species. So it's not inappropriate, I'd say, to do that, but you should always add a caveat, because sometimes it's just logistically impossible to study the entire range of the American robin, for instance. And you think that the effects that you've observed, that there's more robins where there's lawns and grass than there are when that isn't present, is probably something that's going to apply to their entire range. But you should always add the caveat that this needs to be studied in other areas to ensure that these results are valid across the entire range. I've included a copy of figure 1.1 from your text here because I think it gives a good job of showing this trade-off between internal and external validity that I talked about. So if you look at the axes, you go from uncertain to certain along the y-axis, and from small to large along the x-axis. So the x-axis is essentially our inference space from small, say, descriptive natural history studies up to large-scale natural experiments. And along the y-axis, if we stay on the small end, again, we go from descriptive natural history to laboratory experiments. And our certainty of cause and effect increases as you go up. We're going to be talking about some of these other terms that are listed here, like pseudo-replicated field study and replicated probability sample and pseudo-replicated field experiment and so on. We're also going to talk about models, and we'll talk briefly about simulations and theoretical models. And the thing I like about this is that it shows that all of these approaches can be important in helping us understand natural systems. And where we'd like to get is that top right corner, where we have certainty about understanding processes or population phenomenon at large scales. And that's really going to take not just one approach, but integrating many approaches, from laboratory and replicated field experiments to descriptive natural history and natural experiments. And the thing I think this does is it puts all these approaches on a more equal footing. And I believe that you can get good information from all of these approaches as long as you ask good questions and you follow good methodology. And there tends to be some um, feeling in science that certain approaches are, quote, better than others. And there's certain things that certain approaches can give you that others can't. But I think if we really want to understand these complex ecological systems that we're studying, we need to look at many, many different approaches to get information. So let's apply some of these concepts to a hypothetical example in this case. Say you're interested in testing the effectiveness of a new bacterial pneumonia vaccine on Rocky Mountain bighorn sheep. This is the disease that they are very susceptible to and can cause lots of mortality. So it'd be nice if we had a nice effective vaccine. Say your population of interest is Rocky Mountain bighorn subspecies that ranges from Montana to New Mexico. But you have a captive herd of 100 animals in a facility. Um, so that's going to be relatively easy to work with. So you select 20 sheep from that captive herd and give them the vaccine and 20 others that serve as controls. Maybe you capture them and inject them with a saline solution just so they go through the same handling process. 1 month later, you inject them all with bacterial pneumonia to infect them, and 6 months after that, you count the number of surviving animals. So when we think about this bighorn sheep example, the first question that you might ask is, does the experiment have internal validity? In other words, can we make a strong statement about the effects of the treatment that we're interested in? In this case, I think we can say yes. We have control, we have randomization, and we have replication. The second question that might arise, however, is, does the experiment have external validity? In other words, can you take the results that you obtain from this experiment and apply those to, say, Rocky Mountain bighorn throughout the population that we're interested, from New Mexico to Montana? And in this case, I think the answer is probably not. Why not? Because there's many reasons why the particular bighorn sheep that we have used in this study may not be representative of the total population that we want to make inferences to. So the one thing that we often find in captive populations is that many of the individuals in the population are related. We maybe get 3 or 4 sheep initially, bringing them to captivity. They start having offspring, and simply because of logistics, it's easier to just keep those offspring and breed them over time than to try and go out and get new ones. So you may have much more closely related individuals in that captive population than you would in the wild population. There also could be possible effects of captivity, right, which could have negative or positive effects in this case. So, if they've been exposed to a lot of other pathogens because they're being housed with other ungulates in the area, maybe they would be less susceptible to pneumonia. On the other hand, if their diet isn't good, or if there's other sort of stressors occurring on the animals in this captive population, then they may be more susceptible. Oftentimes we find that there's a trade-off between internal and external validity in the studies that we do. It's often hard to implement good experiments to an entire population of interest. So when we talk about internal validity, we're talking about the factors associated with good experiments, like I talked about, control, randomization, and replication. When we're talking about external validity, we're talking about, can we make inferences from what we find to the population as a whole? And we'll talk about this Oftentimes, to make the most progress, what we may need to do is have a combination of good manipulative experiments, which maybe have less external validity, and then good large-scale mensurative approaches, which may have less internal validity, but have better inference to the population that we're interested in. And oftentimes, by using both of these approaches, we can often get to a better feel for how these different factors might be influencing the variable of interest. Well, how about confounding factors in this experiment? Well, age might be one if there's a difference in the age structure of the two groups that you've chosen. That could have an influence. Sex could affect things. Again, if there's a bias in numbers of males and females in the two groups and one sex is more susceptible than the other, that could certainly influence our outcome. Certainly past exposure to pneumonia. If any of the sheep in the captive herd have been exposed, that will give them a much greater immunity. And if any of those happen to go into the control group, that could be a real problem. And I'm sure you could think of lots of other potential confounding factors in this case. Now let's look at another example. The relationship between seatbelts and auto accident mortality. So say we have a database of auto accidents in Colorado from 1990 to 2010. We randomly select 1,000 single car accidents and we categorize those into whether the driver was wearing a seatbelt versus not wearing a seatbelt. And the response variable in this case is kind of morbid. It's whether or not the driver lived or died. So say from the sample, 680 individuals were wearing a seatbelt while 320 were not. Our population of interest here, say, might be auto drivers in the United States. So that's something that we'll come back to. Experimental unit is a single car accident. Observational unit is the driver. And when we analyze the results, say we find that the results strongly support the notion that those wearing seatbelts survive auto accidents more often than those that do not. So the question is now, is this a true experiment? We have a treatment effect, and that is whether the driver was wearing a seatbelt or not. So you might say, well, yeah, we have a nice treatment effect. In fact, it is not a true experiment. It's what we would refer to as a quasi-experiment. Although there's a control, those not wearing seatbelts, and replication, there is no true randomization. Really, to do that, you would have to pick individuals that are driving their cars and say, okay, you put on your seatbelt and wear it for the rest of your trip. You don't wear a seatbelt, and randomly assign that. You can imagine there might be some ethical issues with that. So we just take what we're given. And you think, well, no big deal, just because we didn't randomly assign it, we can still make some strong cause-effect inferences, can't we? Well, maybe not. There might be pre-existing differences between those individuals who choose to wear a seatbelt and those who do not. It's possibly that those that don't wear seatbelts are more often intoxicated. They may be driving faster. They may be in cars that are less safe. So the fact that you find more deaths among people without seatbelts might have to do with a lot of these other confounding factors rather than the effect of the seatbelt itself. So we have to be really careful when we're trying to make cause-effect inferences from quasi-experiments. We can also classify experiments as retrospective or prospective. Retrospective meaning looking back, prospective meaning assigning a treatment and then following it forward. The seatbelt example is a retrospective experiment. We look back at existing data. These kinds of experiments, I'll say, are almost always quasi-experiments because they generally would lack control of assignment of treatment via randomization. There could be some situations where you could have a true experiment in a retrospective study. So say somebody decided to look at the effects of some blood pressure drug on the longevity of individuals after they receive the drug. So maybe 10 years ago, somebody did an experiment where they randomly assigned drugs to a group of people and then looked at how their blood pressure changed over the next year or so. And then later you come back and say, well, we still, we have more information on these individuals. We can now look at their mortality rate over a 10-year period. That would be an example of a retrospective study, which is a true experiment. In our bighorn sheep example, we had a prospective experiment. We randomly allocated the treatments to the experimental units. So in fact, it was a true experiment. There could be a situation where even a prospective experiment is not truly a true experiment if we didn't use a randomization process when we're choosing the individuals to assign. Maybe we just said, we ask for volunteers and say, who wants to take this drug? And we get a number of people that step up and say, I'll take it. And then we compare them to a group that didn't take it. Well, you're really not randomly assigning them in that case. And so, there could be existing differences between people that step forward and those that don't. So there can be some lack of correlation between retrospective and quasi, prospective and true, but I think you know what I'm talking about.